All right. So where are we at? So we were doing panel data last class. I'm going to revisit that before we move on to the last kind of topic, which is IV or instrumental variables. So that's kind of what we'll be doing this week. And next week should primarily be like a lot of review in class. I'll probably go through some more instrumental variable examples to start Tuesday's class, just kind of start reviewing there. But then after that, kind of anything that we've covered since the last midterm, we'll start doing some exam review. So if we look here, where are we kind of currently at? We got one more in-class quiz. Don't have one today, so guess when that's going to be next class. It'll be the last one. So once that's in, I'll kind of get the grades updated. I believe, well, let me make sure I'm saying this right before so we go back and look at the syllabus. Go down here. So those in-class quizzes. Here we are. So I'm going to drop your lowest two. So after Thursday's class, I'll get on Canvas and get it updated so that it shows you what your score is with those two lowest dropped. That'll be kind of your grade in that category. The problem set. So we've got one more problem set that's currently up there. I think I moved it down here is to be in the most relevant stuff because half of it's going to be panel data, half of it's going to be some of this instrumental variable stuff we talk about. So I said start kind of working on that early so we can kind of get that out of the way. I've got the due date set to be a week from today. So make sure you're kind of getting on, starting working on that. We've already covered the first half of it. Honestly, even after today, you probably have almost all you would need to really complete the whole thing. We'll start working on these instrumental variable slides and do file. Other than that, that sixth quiz. So I'm going to add it here so we can all see it here today. Where are you at? There you are. And I'm going to publish it. I don't want you to do this before today's class. That's why I did not post it yet. So it's basically going to be, as long as you get on and respond to the questions, you're going to get all the points. It's more survey based. It's not really like an actual quiz. So here we can kind of even take a look at it. So I have this set to be due the end of the day Monday. Why? Because I want to get this on and get it kind of included into your grades as early as possible so you can get a good idea about what your final in-class quiz grade will be after I drop the two lowest, and then also what your final quiz grade would be, right? Now, the only other thing we would have is that problem set, which I'll try to get kind of graded quickly next week before the final. So you would then kind of have an idea of where your problem set grade will be at going into that final exam as well. So you notice I'm asking you like, did you find the most difficult? What did you find the most helpful? I mean, these are survey. I've got some open response stuff. I realize you could put zero thought into this. By all means, you got to weigh out your marginal costs and your marginal benefits. If you care at all about me and my externalities, right? Maybe put a little bit of time into it and the externalities of future students. So this is my third semester teaching this specific course. And so I'm always trying, my B251, I've taught microeconomics for like 10 years now. So I've got a lot of things ironed out. I've found ways that work, found ways that don't. This is a higher level of thinking, right? It's not easy microeconomics. And so I'm always looking for things that I'm wanting to get responses back from you of what you find helpful, what you find not helpful, things that interest you more, things that don't. So I can kind of cater classes more towards, I shouldn't say cater classes towards the students because I have to teach you what I have to teach you. But it just kind of helps me update the class and kind of make it really, it's like a living, breathing kind of thing to me, right? I don't want to kind of have it come stagnant. So if you don't mind kind of putting some time and thought when you respond to this, but don't also spend, I don't know, if you spend an hour on this, that would be wild to me. But put a little bit of time into your responses here because I do look through them. With my 300-person sections, if I did something like this, I'm not going to lie. I'm going to like put it in Excel and sort it and like summarize it. But I think here I'm going to actually probably read through almost every one of these, right, this summer. So this should also be easy points, though. Should be a way you can kind of pull up that quiz grade. Now, I mentioned, I think last week, even though this was going to be kind of an easier effort-based quiz, you still have the sample questions that would have kind of went along with like a quiz that had actual questions over panel data and things like. So these are good to review as we're kind of getting closer to the exam as well. And then after class today, I've got a practice exam that's kind of sitting there waiting. I'll get that posted as well, so you can start taking a look at that, thinking about what this exam is going to look like. Okay. It's not cumulative in the sense that I'm not going to go back and ask you the types of questions we had in exam 1, but I mean, everything we've done builds, right? I'm still asking you about statistical significance, and I'm still asking you about all these. So it's comprehensive. I always say it's comprehensive, not cumulative, right? So I think that should be all the housekeeping stuff in terms of where we're currently at in the class. You know, I think that at this point, probably beating a dead horse here, but, you know, also this, well, you guys, I don't think I've gotten any emails from you. So hopefully no one takes this personally, because I got some emails and was like, well, Professor Lannis, you posted this hypothetical grade tool and I can't use it. I can't change anything. Why can't I change anything? What do I need to do? Download the file, right? So once again, I don't think that was from any of you. That was my B251 course. I do a similar thing for. I guess shows what a difference a couple of years can make. Also makes me question what the primary education system is doing. But so here I kind of got the weights that line up with this class, the different categories. So obviously these grades, you can start to get a little bit better idea where your problem set grade is once all these final due dates start passing, quizzes, in-class quizzes, and then it kind of updates and shows you what your hypothetical grade would be if you kind of play around with different grades in the final. Okay, so that'd be a kind of helpful tool. I know there's like the built-in what if thing in Canvas. I've tried using that, and do you guys like that? Do you find it helpful, or? Well, I think the problem is like sometimes there's things that aren't weighted on there, and then so then it looks like nothing's changing and it's kind of hard. It's just not organized well. So I always like to do a separate file like this instead of mess around with that what if tool. And then also I'm like creating a final exam that hasn't happened yet. So that's always kind of weird on there. The only other thing I'll mention before we get into material here today, my office hours tomorrow, I'm going to have to move them. So they will be on Friday. I'm still not 100% sure of the time, but I believe it's probably going to be late morning to early afternoon, something like 11 to 2 or 10 to 1, something like that. So look for an announcement about when exactly those will be. I think those kind of moving those from Friday, from Wednesday to Friday shouldn't be a too big of a deal given our due dates and things in this class. But I wanted to mention that before we get started. Okay. Any other questions for me before we kind of dive back into where we left off, which was this panel data stuff? Okay. All right, so I think we left off kind of thinking about this idea of autocorrelation and how we test for it. So I've got a few more examples that we'll just work through with panel data, but just to revisit this idea, because it was kind of towards the end, it's very similar to the problem that we talked about when we have heteroscedasticity in our error terms, and we need to use that robust command that kind of accounts for the fact that our errors, the expected value of our error term, given different values for x, might not be 0. We didn't talk too much about like the logistics of what Stata is doing behind the scenes to correct for that. We just said there's this built-in command. If you really want to know about that, you'd have to take like a graduate level course where you would dive into like exactly what it's doing. Similar to heteroscedasticity, we have autocorrelation in our error terms when we're dealing with panel data. And this is the idea that when we don't have data on things from time period t, those are likely to be correlated with the stuff we don't have data from in time period t-1. So if that correlation exists, and there's a strong correlation across those time periods in that error term, it's going to screw with our standard errors. So one kind of issue one command we can use to resolve this issue is going to be not clustering our standard errors, but use what we call robust standard errors. So we'll see what this kind of looks like in Stata here, and how to test for whether or not there is autocorrelation. Okay, so I think we went through these examples with birth weight last class. Here. Right, we didn't do the unemployment rates. Oh, actually, I've got a fun example. Let's do that one. Yeah, that's a little more interesting for today. I throw in several examples. We can kind of use this one here today. So I've got this fatality data. let me make sure, because I might not have thrown this up on. Sure enough, I didn't. So let me go ahead and add that. So if anyone wants to work along with me, you can. Because I think this will be a fun data. Well, I should use the term loosely, right? So week 3, gonna go here. I think I forgot to drag that. Oops. There we go. And then just so it's easier for you guys to find, you don't have to hunt through the files tab. I'll add it under the panel data. There it is. All right. So I believe this data set's like a bunch of traffic fatality data. So we're getting real morbid here today. But it's kind of interesting. So let's say I have this really naive regression, and yeah. I don't know if it's just this should just be the panel data post. This is the one I posted. The other one has some stuff specific to me. Sorry if that wasn't, it's the same panel data do file that we used last week. Let me make sure that I included the additional example in there now that you're asking me. I'm second guessing myself. So let's download this real quick. Are you guys seeing the all mortality stuff at the end of it? Let me see here. So if I look at post. Oh no, I left it off. So this is the one I just had for class. Okay, well, we'll do the one that's not as interesting. And if we have time, maybe next week I'll save the mortality one. So let's use, you guys should have the GDP data. Okay, we'll use that example. No, sorry about that. We'll use the GDP instead, okay? So instead of the all mortality or the fatality one, we'll do the GDP. It's, it's economic related, but, right? So we'll kind of be using this GDP class data file, okay? And if we have time, maybe I'll even get this do file updated and we can kind of go through another example. So we'll do this naive regression where I'm going to use the unemployment rate and I'm going to try to predict it using income. Okay, so I believe this is kind of all at the state and county level. So here, I'm going to run this regression. This is going to be kind of our baseline, right? So if I run this regression, I don't include any fixed effects, I get this estimate of what, negative 0.075. So every time income in a county goes up by, I believe this was set to be kind of the average, so it goes up by $1, right? I think the unemployment rate's going to go, no, there's no way that's true. Income must be in thousands here, right? Yeah, all right, 66 would be like 66,000. So every time average income in a county goes up by 1,000, the expected unemployment rate goes down by 0.07%. So it's a pretty small amount. So here instead, let's say, okay, we want to control for all this stuff that we know varies across counties and states, but we don't have data on it. So what I can do is try to set up this as a panel data set. We said the command we'll do for that is xtset. Now, I can try to set this up so that I have an identifier or a dummy variable for every unique state and county combination. So I might think, okay, I can just use the xtset, state, county, and then year, right? So I've got every state and county and a bunch of different time periods. This is going to give me an error term. So I can only use, the way that Stata has this set up, I can only use 2 variables with xtset. Now, what could I do? Well, if I've got the state and county data, I can actually create my own identifier. So I wouldn't expect you to do this like on your problem set. But here, if I've got state counties, what this command will do is say by every unique state and county combination, create this variable. And when I do underscore n equal 1, it puts a 1 for the very first observation for every one of those state county combinations, right? So this becomes pretty useful when I've got panel data sets where I've got multiple things. So I've got a bunch of like NBA shot data, NBA playoffs are going on right now. Maybe I want to use a unique team player. This would put a 1 in for every team kind of player combination. Right? So here, I'm going to create that. Now I can kind of see every time I've got the very first year, for a state county, there's a 1. New state and county, the first year, there's a 1. Every other time period, there's a 0. What I can then do is by this unique variable I've created, this underscore n starts to say, okay, the very first time I see a 1, put a 1. The next time, put a 2, 3, 4, 5, 6, 7, 8. So for every single time, it's going to have like a 1, a 2, a 3. It's starting to create a unique identifier for every state county combination. Okay. So I'm going to go ahead and do that. And I'll see here, okay, here's all my missings. Because it's only going to do it for the very first observation of every state and county. So notice here, like Pendleton, Kentucky gets the identifier of 1. What, Birdie? I didn't know there was a county named Birdie. Birdie, North Carolina, there's a identifier of 2, so on and so forth. Then by every unique state and county, I'm going to take the maximum of that identification variable. Now, okay, King, Texas, every time I have an observation that's in that county, it's at 815 is the identifying number. Texas, Kinney, every time I've got that, I've got the unique identifier of 2,309. So I've now created a number that represents every unique state and county, and I can use that in my XTSet command. Okay. So just because you've got like multiple levels in your panel data set, so here it's state and county, it's not just state, right? Or it's not just country, like the example we used last class. What I can now do is check to make sure by this new state county variable I've created, do I have a balanced panel? We said, how can I do that? I'm just create a variable that's 1 for every observation. Then by every single unique county identifier I created, add up the total number of count var, add up that variable, which is always a 1. So that should tell me the number of total years I have for every state and county. And then tab just kind of lets me see what values I have for it, right? So if I run that, now I can't remember if I was talking about, yeah. Every single county and state unique combination here, I've got 7 years of data on. So this would be a balanced panel. This would not be balanced if I use the tab command and I see that, oh, some of these state counties I've got 7 years, some I've got 6, some I've got 5. That would be an unbalanced panel data set. So here we've got a balanced panel data set. Now I can use my XTSet command. By state county, this new unique number I created, and by year. So I'm going to go ahead, run that. So now I've got this set up as a panel data set. Now, if instead of using just the regular reg command, I use my xtreg, I can put this option at the end. Now, my original, oh, yeah, I've got it here. So I'll show you the problem, and I hopefully won't break this computer because I don't know what its memory is. Memory space, not its memory. So my original regression was just unemployment income, and we had what, negative 0.075. I could use the IDOT command, and that's essentially fixed effects. There's a dummy variable in there for every unique state county identifier. The only problem is if I do that, it's going to take this a while to think. Right? In fact, I don't know if it's ever going to run because how many counties we had? It was something in the like 2000s. This is just a very inefficient way of coding it in Stata. So I'm actually going to hit this. Hopefully you weren't following along at this part because I don't want you to stop your computer. It's going to take forever to run. So I hit that X button. I don't think I've ever used that in this class. What that does is it just stops Stata and says, whatever you were doing, just leave it alone. It's taking way too long, right? So instead of kind of using that IDOT command, we're going to use that xtreg and put this comma fe on the end. It does the exact same thing. I'm trying to think how to explain this. It just does it behind the scenes in a more efficient computing, the way that it needs computing power, it does it in a much more efficient way. So that it'll run a lot quicker. So sure that was grammatically completely incorrect the way I said that, but the idea is it does it faster, right? So sure enough, it's already ran before I can even get done talking. And now I see my coefficient estimate isn't negative 0.075. Once I've controlled for all of the omitted variables that vary across state and counties that I don't have information on, I'm getting an estimate that's quite a bit higher, right? Almost 4 times as high, and it's still negative, right? So it didn't change sign, but it could have, right? So I've now got a much higher estimate for this relationship between the average income in a county and unemployment rate. Okay. Everybody with me up to this point? Okay. So once again, I could set this up. I've already done this, so I don't need to run this again, but I've got this set up as a panel data set by my state and county unique identifier and then the year. So one thing we said we could do, and we wouldn't need to do this if we didn't want to then test for autocorrelation. We could just run that simple fixed effects command. But we said another way of doing this is really looking at kind of your first differences, right? You could run that regression. So we said, once I have this set up as a panel data set, how could I find the change? So just to kind of write this out, what we're doing, instead of like running this regression where I look at and then I included all my fixed effects here, right? Instead of doing this, what I could do is look at the change in my unemployment rate and the change in my income, and then I don't need to include all those fixed effects. Now that should give us the same unbiased estimate for beta 1, and we'll talk about an issue that's going to exist with this here in a second. So how can I create these change variables? Really what I'm doing is I'm saying, take the unemployment rate in whatever the current year is and subtract whatever the previous year would be. Okay. So how can I do that in Stata? Well, I'm going to create this new variable, which is the unemployment rate difference. I'm going to take the current unemployment rate and subtract the previous year. So once I have this set up as a panel data, the way you can just go back one time period and make sure that you're looking at the same state and county is if you use this capital L dot, right? So this says, look at this observation's unemployment rate, subtract the lagged or the unemployment rate and from that same state and county, but the year before. So that's going to calculate our change. I can do the same thing for income here. If I do that and then run this regression where I'm looking at the change in my unemployment rate and the change in income, hopefully, unless I'm lying to you, we should see the same coefficient here. Okay, so I'm going to go ahead and run that. Okay, so I've got a slightly different value here, right? So why did I come up with a coefficient estimate that varies? Oh, where's that? With this, right? Well, for one, right, we're kind of looking at that. Oh, sorry, what did I do here? I wanted my first difference. What did I not? So I generated the unemployment rate, income. Oh, I wanted. Where's this at? Fixed effects. State, county, year. Is that the same thing I have up here? Well, it should give me the same estimate. Why it's not doing the right what I want to do? So I use the lag unemployment rate, lag income. Make sure I set this up correctly. Let's try this again. I think I forgot a line of code. So let's try this. Oh, I've got to create it. All right, so let's run this down here. Regression. What am I forgetting about here? Forgetting something I can't think. Oh, because okay. Scratch that. Don't worry about the first difference. You can run the first difference approach. Sorry, you're not going to end up with the same coefficient estimate. You're actually definitely going to end up with a different coefficient estimate. It's not quite the same thing as when we were looking at those fixed effects. Okay. So the reason why I kind of have this set up so we're creating these difference variables, and you can do this a slightly different way. So let's say, I'm just going to call this a second version of it. You can actually use this d dot command. And then I'm going to do the exact same thing. but I'm going to do it for income. That is not allowed at all. All right. So I can use kind of the method where I use the lag, or I can kind of use this D dot. If I use either of those, hopefully what I find here, we can kind of see we're getting the exact same values here, right? So it's just a different way of coding the variable. Kind of, you can take the current, subtract the lag, or that's essentially what this D dot command does. Right? So two ways of doing the same thing. Now, if I run this regression using my first differences, I end up seeing this is my coefficient, right? Now, the problem is I might have autocorrelation in my error terms that we haven't tested for yet. So when I was telling you about using the first difference to fix effect, that was if we didn't have autocorrelation. I forgot I have an example here. I was trying to show you eventually autocorrelation, which is we actually have some. So how can I kind of test for that? So if I run my first difference regression, I then predict my residuals. So this is just going to be the error term from that regression. So look at the actual kind of change in the unemployment rate, and then subtract whatever the predicted change would be, given my X variables. The only X variable we have here is that change in income. So I'm going to save those residuals, right? So this would be like the difference between the actual and predicted change in that Y variable, which was the unemployment rate. I'm then going to run a regression of those residuals, so those values that I've now created in this variable. Yeah.
Wait, so sorry, how do can you show me the variables that it's taking the difference of? Like,
So if we've got Nebraska, let's see if I get this all in one. Yeah, there we go. Oh, maybe not. There we go. So like if I take this observation here, if I can select it, how is it coming up with the change in the unemployment rate? It was taking the current unemployment rate in Hall, Nebraska. It was then subtracting the year before unemployment rate in Hall, Nebraska.
Yeah.
So that change should be -0.5.
yeah, sorry, I meant like the residual.
So the residual is what it's doing. It's kind of doing this a little bit behind the scenes. But if this is the regression that we run, right? Whatever these estimates are, we could plug in different value. This is just like what we were doing before with an X and a Y variable. I could plug in different changes in income, and I could get different predicted values for my Y variable, which now is the change in the unemployment rate. What my error term, or what my residuals, this is kind of the word that state is using, would be is if I take the actual change in my unemployment rate and I subtract that predicted change using those coefficient estimates. So it was just like when we had just Y. Remember, our error term was just the difference between the actual and predicted Y. That's all that residuals command is doing. It's just calculating these predictions behind the scenes and then subtracting them from the actual Y values. Does that make what you're, sorry, I misunderstood your original question.
No.
Okay. So when we run that first difference regression, that's what we're saving as those residuals, that error term. Well, what was autocorrelation in error terms? It's when the current year's errors are correlated with the previous year's errors. In fact, not only did we say they have to be correlated, we said it's going to be that it's something different than -0.5, right? The correlation, if it's different than -0.5, that tells us we have autocorrelation in our error terms. Now, one of the other things that we had to do, and it's kind of weird because clustering is something we haven't, it's kind of weird to test for this. You have to actually talk about something that you then would use to kind of help you in the solution for if we have autocorrelation. But when you run this regression where you look at the current error term or residuals and you regress that on the previous year's residuals, you need to, in that regression, and no other regression we've talked about, or we would have any reason why, we don't want to include a constant. But in this regression, because we're just looking for, is there kind of this correlation between the residuals, we want no constant in our regression. So that's what that command does. And then we're going to cluster our errors at the state county level. So what this kind of does, it accounts for the fact that We're just looking to see is there a correlation between the error term from this year and the previous year within each state and county. So we recognize there might be differences in the errors that exist in like New York's unemployment rates, error terms, compared to, Bloomington, right? And so that's essentially what clustering those standard errors will do. So you would always cluster them at whatever you've set the panel data up as, right? Here was our state county. So once we run this regression, we'll see this coefficient. Now, it's something other than 0, but we actually want to test for here, not is it different from 0. We want to test for is it different than negative 0.5, okay? So if we run this test where instead of comparing it to 0, so the p-values we see here, that was testing it against 0. We want to test it against negative 0.5. Now this one, if the test against 0, this gets maybe a little bit tricky. So typically, when we're running these hypothesis tests, we had some statistics. So here we're looking at write it out in different ways, given what we've talked about. So we came up with this coefficient estimate between the residuals and the lagged residuals. Usually we were subtracting the hypothesized true value of 0 and then dividing by the standard error to come up with our test statistic. So if we did that, the regression results would give us the p-value with the assumed true value of 0. Now we're running a test where so the results that we were given, this p-value was basically 0. If I instead do this test, so I found beta, I think was like 0.11 here. If I'm then changing this to negative 0.5, is 0.11 going to be further away from negative 0.5 than it is from 0? Well, how far away is 0.11 from 0? 0.11, how far away is it from negative 0.5? 0.61. So my standard errors haven't changed, but what's happened to the numerator? It's went up. So my test statistic is going to be higher, which means my p-value should be even lower, right? So if I see a p-value of 0 from that initial regression of my residuals on the previous year, I automatically know I'm going to be able to reject. However, I can prove this to ourselves by actually running the test. Sure enough, like we're getting a p-value. I mean, we can't really see any difference, but it is going to be closer to 0, right? In fact, if you just look at the test statistic, it's a slightly different regression, student T versus kind of F, but high sample sizes, these converge. So we're ending up with a much higher test statistic here and a smaller p-value. Okay. So we definitely can reject, right? So if that coefficient estimate is negative 0.5, so if we could fail, like we're assuming that it's negative 0.5 with that test, if we couldn't reject that, we're saying that we found evidence that there is autocorrelation. So we're trying to prove that there isn't. We stack the deck against ourselves and assume that there is autocorrelation. If there is autocorrelation, that correlation should be negative 0.5. So we are rejecting that and saying, we can say that it's not negative 0.5. We found something that's statistically significantly different from negative 0.5. So we found strong evidence that there's no autocorrelation. So we don't even need to worry about this. We don't need to adjust for this. Okay. Excuse me. Now, let's assume that we did, just for the sake of kind of running through an example of what we would then do. So if I wanted to, and here I think I included the year instead. We don't need to, because we were looking at an example without year, and I'll show you what it looks like with year. So let's say I'm running this regression, and I set this up as a kind of panel data set. How would I cluster my standard errors? Well, first of all, I'm going to kind of run this with my fixed effects. And I can see here, all I'm going to do is add in this option at the end, which is VCE, and cluster those standard errors. Okay. So if I go ahead and do that, kind of notice it'll run, and my standard errors from the regression, 0.003, here they're 0.008, but I'm still getting the same coefficient estimate. So by clustering those standard errors, I haven't changed the coefficient estimate at all. I've just changed those standard errors. So I've just changed my rejection decisions. Okay. So notice here, if I look at my original regression, my test statistic's -30. Or no, it's not. I didn't scroll up. It's -74. So typically, and this won't always be the case, but typically if I don't cluster my standard errors, they're usually going to be higher, right? So in this case, or sorry, my standard errors won't be higher. My test statistics is going to be higher. So my standard errors would have to be a little bit lower. So if I don't cluster for my standard, cluster my standard errors to fix for this autocorrelation, notice my standard errors here, 0.003, test statistic of -74. If I cluster them, doesn't look like it goes up by much, but 0.003 goes up to 0.008. That's more than twice as large, almost 3 times as large. Greatly reduces my test statistic. Now, in both scenarios here, my p-value is 0, so it wouldn't have changed my rejection decision. But you can imagine a scenario where maybe I start out with a test statistic of 3, and then it would decrease down to 1. That might give me p-values where I would then change my rejection decision. So kind of the process that we're going to use here is you'll run that first difference regression, save your residuals, run a regression of those residuals on the previous year's residuals. We don't include a constant, and then run this test to see, is that coefficient or the correlation between those two errors, the errors and the lagged errors, is it anything different than -0.5? If it is, if we can say it's statistically different than -0.5, we found evidence that there's no autocorrelation. We don't have to do anything. If we didn't, we should be adjusting for it. Now, we can adjust for it either way, right? It's just that this is going to be a strong evidence that we really need to make sure that we adjust for it. Any questions on that before we continue here? And I think I did this one. Let me see if I put it in the commands. Yeah, so just to kind of go through another example quick before we move on to instrumental variables. If I did use this fatality data, don't worry about going along with this. I'll probably pull this up next class and do a little bit if we have some extra time. So this was just a different example. So I run the naive regression. I'm looking at the effect of beer taxes on traffic fatalities. So when taxes are higher, it actually looks like more people are dying than traffic fatalities. It seems kind of weird. Well, maybe it's because I haven't accounted for all these things that vary across state and times. Maybe states with higher beer taxes also tend to have, I don't know, more, fewer people drinking, right? And so there aren't as many traffic fatalities. So I'm going to set this up as a panel data set, just state and year, and include my fixed effects and my coefficient. Wow, changes a lot, right? I'm now accounting for everything that is specific to a state that doesn't change across time. I'm controlling for a lot more. End of the day, these fixed effects models, all you're really doing is eliminating omitted variable bias. So the omitted variable bias that we eliminated, our coefficient estimate now is -471. So increasing the beer tax actually reduces the number of traffic fatalities. Hopefully, the idea economically is fewer people are drinking or drinking less. And so you wouldn't have as many drunk drivers. You won't have as many traffic fatalities. Now, we could also do a very similar test for autocorrelation here. So I just use the ddot command here. I think that one's easier, right? All you have to do once you have it set up as a panel data set, if I want to find the difference in mortalities, just use that ddot command, and it'll take the current year's traffic fatalities minus the previous. And then beer tax difference, take the current year beer tax minus the previous. Okay. So if I do that, I've now got my two differences. Now notice here, it tells me I've got a bunch of missing values generated. What's one, here I'm using this to test for autocorrelation. If instead of running a fixed effects model, I did use the first difference approach, what was one issue that we had talked about? What am I going to lose when I use that first difference? So the very first year of data, when I try to look at that year minus the old year, where's the old year? Not in my data set, right? So I'm going to lose a lot of observations, right? So that is going to change my estimates, my standard errors a little bit. But that's the approach that we have to use to test for autocorrelation. We need to use those first differences. So I'm going to run that first difference regression, predict kind of the error term, and here, kind of notice, you can actually shorthand this. I think I spelled it out in the previous example. But if you use this predict command, instead of spelling out the word, Stata actually identifies it if you just put an R in there. I didn't put it the first time because it's like a little more black box. It's kind of hard to know exactly what it's doing, but you can use kind of, instead of typing out the word residuals, it knows what you mean if you just put R in here using the predict command. We're then going to run that regression where we cluster at the state level. We've got no constant, and we're looking at the current residuals and the previous year's residuals. So my coefficient estimate here, okay, well, it's negative 0.12, which is different than negative 0.5, but it's closer than in our previous example. So I'm going to run this test to see, is it statistically different from negative 0.5? Looks like it is. So this would be evidence that I still don't really need to completely worry about autocorrelation, right? I'm not rejecting, or sorry, I am rejecting at high levels, which what do we assume? We're starting out assuming that there is autocorrelation. So if I can reject it, it means there isn't any. Yeah.
Neither, I mean, like, in that other example that we did, we didn't have this stuff for autocorrelation in it. Do you think you could post that at some point?
Oh, you did? Up here?
Yeah, no.
Oh, yeah. I'll make sure I get this updated. Sorry, that should. Is that not in here? Oh, nope, it got left off. Oh, yeah. Well, thank you for saying something. I thought I kept all this stuff in there. So this is, I'll make sure I get this file updated so that you have everything that we kind of had here in class today.
Thank you.
And then once we have that, if we do cluster our standard errors, we can go back to the original regression. Originally, our standard errors were 115, coefficient estimate of negative 31. If I'd run the same regression, fixed effects, but I cluster my standard errors here, I'm getting negative 471, which is the same coefficient we found before we clustered the standard errors. I might have been, sorry, I was pointing to this was my first difference regression. The original regression we had, which was fixed effects, we had a coefficient of negative 471, standard error of 97, right? Once we cluster our standard errors, shouldn't impact our coefficient estimate, but our standard errors have changed quite a bit, right? So what did I say before they were before 97? No. Yeah, 97. Here now they're 167, right? So notice here, you can start to see originally our p-value was 0. Once we cluster our standard errors, we're getting something that's a little bit lower, right? Now here it would still be less than all of our conventional levels, but you can at least see it starting to move in a direction where maybe once you cluster for the standard errors, you might actually lose statistical significance compared to when you didn't account for that. Okay. All right. I will get this posted with all the code here. Sorry, I thought that was attached to that file that I put up there. I had some things in here that I didn't want to kind of muddy up the file with too. I just want to use it for class. So I'll make sure I get the one that's cleaned up, kind of added to the end of this panel data post and re-upload that. Okay. All right. So that should kind of rehash this idea of panel data sets using fixed effects. The other thing that we want to talk about, we'll kind of start today and kind of finish this off Thursday, is instrumental variables. Right? So we kind of talked a little bit about some of these things, but fixed effects was one solution to the omitted variable bias problem. I briefly mentioned we were talking about data issues like measurement error. So if we've got I put errors in variable here, measurement error in variables, or if we have some simultaneous causality. So we didn't focus a lot on this because we hadn't have any tools yet. But I think I had a slide where I said, you know, what if X causes Y, but then as Y changes, that is also going to change X, right? So this is like the common problem of, if you really think about trying to estimate a demand curve, if there's higher demand, right, what's that going to do to the price? Increase it. But once the price increases, what's going to happen to the quantity demanded? It's going to go down, right? And so it's going to be this counter-cyclical, like this simultaneous causality. We have a solution to that, which is instrumental variables, right? That allows us to kind of estimate some of these things like a demand equation. Right? So just some of the kind of general terminology we'll use. We're going to break our kind of instrumental variable approach down into two parts. So if we want to estimate the relationship between two things, and let's say just for the sake of example, we know there's some omitted variable bias that exists. We want to look for an instrument that is correlated with the error term, right? And then part of it's going to not be. So kind of if you think about what's in that error term, so any variation in X, so the variable that we've included in our regression, that's uncorrelated with our error term, That's really what we need to be using to come up with our estimate. So we're looking for what we call an endogenous variable, something that is going to be correlated with our error term. So this is going to be omitted variables that we might not have in our regression. We need the instrument to be what we say is endogenous to our model, or it would be correlated with whatever's in the error term that we don't have data on. So if I'm like predicting, you know, if we go back to like that all mortality, and I'm looking at instead, what's the impact on traffic fatalities of the average alcohol consumption of a state? Well, I know what's going to definitely change alcohol consumption, the beer tax. So that might be a good instrument, right? It's going to be something that's endogenous to my model. It's something that's going to be correlated with that error term, right? It's going to explain some of the variation that I see, right? Because if I don't account for it, it is going to be something that's then impacting the traffic fatalities I see. So that would be the idea that it's endogenous. Now, we also need it to be, we'll say exogenous, right, to the actual X variable we're including. So endogenous, exogenous, all endogenous means is that it matters, right? It is correlated with something. Exogenous means that it's uncorrelated with, okay? So the two criteria that we're going to need one of them to be endogenous, one's going to be exogenous, and this is kind of our definition. So our first requirement is that we need whatever instrument we're using, this other variable z, it needs to be endogenous, right? Or correlated with the X variables that we are including. Okay? So it needs to be, if I'm looking at alcohol consumption, that beer tax, if it was a good instrument, it needs to be not, sorry, I'm saying this backwards. So endogenous, sorry, what do I want here? Z is, yeah, so I want this to be anything other than 0, right? So I want it to be endogenous, right? Or correlated with that X variable. So if I'm looking at alcohol consumption, I want the beer tax to be correlated with that, right? I want it to be endogenous. I want it to be playing a role, having an effect, okay? So what is having an effect? A covariance, anything other than 0, right? So that X variable you're including, in my simple example is like alcohol consumption. If Z, the instrument, is a good instrument, like a beer tax, it would be correlated with alcohol consumption. Well, for that example, it seems likely, right, that higher beer taxes are going to change alcohol consumption, right? At least, you know, maybe not going from nothing to something, but right, at least on the margin. Now, we also need the instrument to be what we say is exogenous or uncorrelated with our Y variable. So I would need beer taxes to be uncorrelated with just the overall level of mortality, traffic fatalities, right? Other than its impact through X. So it can still be impacting my Y variable through its relationship with X. So in my example, the beer tax, how is that likely going to influence traffic fatalities? Only by changing alcohol consumption, right? So it can still impact my Y variable through the X variable I've included, but it can't be impacting that Y variable through any other method. You might be able to think, so that instrument, it shouldn't be correlated with anything else that's not that X variable, that is not alcohol consumption. You might be able to think of a reason. I can't think of a good story how beer taxes are going to change something that would then impact traffic fatalities other than its impact on alcohol consumption, the X variable. Maybe what would be a likely story there? Well, if beer taxes are pushed through at the same time as, I don't know, speed limit restrictions, well, now my instrument will be correlated with something I'm not controlling for, which is speed limits that would then also impact traffic fatalities. So that's kind of, I don't know why that would be the case, why the government would work that way. But if that was the case, now it's no longer going to be exogenous to that Y variable, right? It's going to be impacting that Y variable through other means other than the X variables I've included, okay? So why should we not necessarily, like before we were talking about instruments, if I had an instrument and it's not correlated with my error term at all, why would I not typically include it in my original regression? So if it's not correlated with my error term at all, if I include it in my regression, what's going to be true about its statistical significance? Probably won't be. Won't be. So I would think I don't need that variable. However, by including it, even if it looks like it's not having an effect, because it's correlated with that X variable, it's going to control, it's going to kind of pull out, right? Once I include it in my regression, it's going to pull out part of what used to be in the coefficient on that X variable. It's going to pull out part of that effect once I can run this instrumental variable. So what are we going to do, right? So how do we run this instrumental variable? Once we have these conditions met, and we'll talk about some tests for these conditions on Thursday. A lot of the times, to be honest, thinking about these instruments is just like more intuition, right? Let me think of another good example that I've heard of instruments. So a lot of the times it'll be things that are completely random. So let's say that you think performance in this class is improved by taking 370 closer to when you take this class. So like taking it the previous semester is going to be better than if you would take, so the time in between is going to be kind of that X variable you think matters, right? But when you take 370, it might be completely random, just the needs of the class. You might get in your first semester, you might not get in till your third or something like that. So a lot of the times with an instrument, you'll exploit the fact that there's like randomness. Like, yes, we know that having 370 closer to 371 would be more beneficial, right? However, there's going to be variation when people take it that is completely random. So you know that randomness when they've taken it, that shouldn't be correlated with your actual performance in the class at all, other than through when you, like, the X variable would be when you took it, but like there's no other contributing factor of when you took it other than just complete randomness, right? So you can kind of think about that might be an instrument, right? Something that is just completely random. So it still has variation. Some of you have taken the class the previous semester, some 2, 3 before. But as long as it's not correlated with any other characteristics of you, that randomness you can use as kind of an instrument, right? Because it shouldn't be correlated with your error term at all. So I'll kind of bring in some other examples. I'll hunt through some interesting ones. I know another one that people really like to use is so if you're looking at like test performance of like ISTEP data, or if you're not from Indiana, like some standardized test when you're in elementary or high school, a lot of times what they'll use is to look at what the impact of different things are. So this might be the impact of your ISTEP scores on, or hours studied on your ISTEP scores or something like that. What they'll use as an instrument is when your birth month was. And I'd be like, why does that matter? So if I'm born, every state's a little bit different, but if I'm born like in August, I might turn 5 right before school starts, and I might be eligible to start school. But if I was born in September, and I have to be 5 when the school year starts, I can't start that year. I have to wait an entire year, in which case I'm no longer 5. I'm actually almost 6, in which case I'm going to be starting school at a much, a year or an age where my mental faculties are a little bit more. So like every first, second, third grader are not going to be the same, right? They're going to have the same years of school, but some of them started at different ages. And so they'll use that birth order because it's going to dictate, like, it's no fault, no choice of the student. It was just completely random when they were born and when they actually started school and what their age was then in each different grade, right? But I'll bring in some other examples next class. I've got some sitting around, some old papers, and we might actually kind of look through those that are kind of interesting. But this is kind of the general idea of these instruments, right? So the procedure that we're going to use is once we've identified a good instrument, So with the endogeneity and the exogeneity, two conditions are met, right? So it's going to be endogenous to our x variable, right? It's correlated with the x variable, but uncorrelated with the error term of our regression for y, or an easier way to think about this, just uncorrelated with y. So we want an instrument that's correlated with x, uncorrelated with y, okay? If those conditions are met, we'll then run this regression where I'm looking at my x variable now. I'm going to make it the dependent variable. And I'm going to try to predict it using my instrument z. So I'm going to run that regression. I can then use those coefficient estimates to make the predicted values for x. Okay. So once I have my predicted values for this x variable, the second stage is I'll run those original y values of, because the original thing I was interested in was the impact of x on y. Right? I'm just using this instrumental variable approach using z to make sure I don't have a bias coefficient. So once I come up with these predicted values for x, I'll go back, run what would be like our typical usual regression. I'll use the actual values for y, but instead of using the actual values of x, I'll use the predicted values of x from my first stage regression where I was using the instrument to predict x. Okay. So you can kind of think about it as I've used this instrument to come up with the predicted values of x. You can almost think about like the original x values had some measurement error in them. What was the measurement error? It was whatever the effect of that instrument was. So by running this first stage regression and predicting those x values with my instrument, this is not technically exactly how it is, but it's a good way to think about it. It's almost like I pulled out that measurement error from my x variable that's associated with this instrument. So once again, tell that to like a high level stats person, but that's not exactly what's happening. It's not, but it's a good way to think about this, right? My instrument is like pulling out that measurement error that kind of would have existed in those original x values, and I'm just using those predicted x values.
So why are we using pi as?
You could write this as beta. It's just so that you don't confuse these. You could use sigma. You could use, well, probably won't use sigma because that's summation and a lot of things that we do, but you could use gamma. You could use whatever Greek letter. You could use, yeah, it's just a way to differentiate that these are the coefficients that are coming from the first stage regression. Here's my coefficients coming from the second stage. Was that what you're asking? Yeah. And if we do this, we should end up with an unbiased coefficient estimate. Okay. So I think here, I'll save this for next class because this is getting a little bit into the weeds. And we've got 15 minutes, so I want to make sure we get an example of this in here. So I've got the IV health. So let's see here. We've got this IV health data. That's the one that I'm going to be opening up. Oh, did I not move it to my OneDrive? It should be sitting there. Oh, I might still be in week 13. I am. So open up that IV health data. I just had it sitting here. I needed to. I didn't have my global set. This actually needs to be a week. I don't really need to do this, but what I probably should have done, I'm trying to show you good practices. So if you have to use a data management program outside of this class, I was in my week 14 file. So I should have been kind of setting my global and then opening up that data set. Oh, why is it not opening it up? If I have the wrong name. Yes, I capitalized it when I posted it for you guys. So this is IV, oops, health. Now I should be able to go. There we go. So I've got this health data. If we take a look at it, so I've got like medical expenses, whether the person had health insurance, their age, gender, some race identifiers, income in the thousands, et cetera, okay? So I'm going to run this naive regression. So when I was setting this up and kind of thinking about maybe like my beer tax mortality example, I was kind of saying I only had one X variable. You can do this and still include controls. So you can use an instrumental variable approach. And just because you're interested in the effect of one of those X variables on Y, you can still add in additional controls. So here, I want to focus on kind of my health insurance. So what does health insurance impact on my medical expenses? So I think here I had the natural log of medical expenses. We won't worry too much about that today. It's just that there's some nonlinearities. So if you don't use the natural log, you get some really weird estimates. So here we're looking at the natural, or we're taking the kind of log of medical expenses, and we want to know the impact of having health insurance. Well, if I have health insurance, if these medical expenses, what would you initially think? So if I ran this naive regression, this is kind of weird, but who has health insurance? Who's more likely to have health insurance? Sorry, I'm not asking you who has health insurance. Sorry, I speak sometimes and think like an economist. Who would be more likely to have health insurance? Higher income, but even if I'm high income, I'll tell you what, I lived a long time before I met my wife without health insurance. Why? Because I was generally pretty healthy, right? So me not having health insurance, what impact does it actually look like it's going to have on my medical expenses? It looks like it's actually going to lower them, right? But it might not been because I didn't have health insurance. It's because if I would have gotten health insurance at the time, it might have looked like it was that, but it's not because I had health insurance. It was because I didn't have health insurance because I was already healthy, right? So if we run this regression, we might get some weird results. So sure enough here, if I have health insurance, it actually looks like my medical expenses are higher. Why? What types of people have health insurance? People who are likely already originally going to have higher medical expenses. So we need to somehow account for that, right? Now I don't have necessarily, I've got some illness data here. Age is going to let me know how healthy, well, not completely, but some measure. But there's likely a lot of other things here I'm not capturing, right? Like pre-existing conditions or some of these other, I can't control for that. Right? So if instead of running this kind of naive regression, I'm going to try to use what I think is a good instrument. Okay. So the instrument that I'm thinking about here is going to be the Social Security income ratio. Right. So this is going to be something that how much money people are given relative to their income might impact their health insurance decision. That seems highly likely. That seems like I've got an instrument that is endogenous to the X variable I'm interested in, which is the decision to get health insurance. Now, the Social Security income ratio set by the state, that's what this is representing. How should that impact my medical expenses? Well, other than through my decision to get health insurance, right? Because I might have more income to do so. I can't think of a good reason why that state level policy is going to impact my actual medical expenses at all, right? So it's only going to be impacting that Y variable through this X variable we think that it's impacting, which is the decision to get health insurance. So I'm going to run my first stage regression. And notice unlike the slides where I didn't have any controls, I can do all of this, but I still need to make sure I'm including all of these other things that I'm trying to control for. So here I just had illness as age income. I'm going to use the state level policy on the Social Security income ratio. I think it's going to impact individuals' decisions to get health insurance. Sure enough, it's statistically significant. So we'll talk a little more next class. That's one of the key indicators we have that this is an endogenous variable, right? It is impacting that instrument Z, the Social Security income ratio, is impacting our X variable, right? Because statistically, I can say that there is some relationship between them. Okay. I'm then going to use that predict command. Well, we've already done this before, where I'm just going to take that regression and we said we're going to predict that X variable or predict the values for whether or not someone gets health insurance. Okay. Now, the command we said would predict XB just gives me those predictions using those coefficient estimates. So all that's really doing is taking the estimates we find from that first stage regression, plugging in the values for the instrument, except for now we've actually got the added controls as well, and coming up with a predicted value for whether or not the person has health insurance. That's what this is doing. So we're going to go ahead and do that. Now, I would likely, so like here, it's probably a better thing. Instead of calling this first stage, I was using this to kind of show you so that you can kind of see we're using the first stage regression or first stage predictions. I might call this something like, well, I don't want to erase this. So I'll show you a different way. Just like, this is very nitpicky, but I would probably, you could also call this predicted health insurance, right? That's what we were doing in that first stage, was we were predicting that X value using the instrument and the other control variables. So it's really the same thing. I'm just calling it something different here. That's just a different name. So now my second stage, I'll use those first stage predictions, still use all of my other control variables. And now I'm going to look at the regression between medical expenses, my original Y variable, and the predicted X values. So before, when we ran the naive regression, we were getting positive 0.075. Now, after we use the instrumental variable approach, well, now it's negative. And this makes a little more sense, right? Because this first stage result, remember, it's still representing the predicted values of whether or not I have health insurance. So here now it looks like having health insurance is actually going to reduce my medical expenses. That makes a little bit more sense. But it's because by using this instrumental variable approach, we've accounted for all the other important omitted variables, like essentially what your underlying health was from all these other things that were unrelated to the Social Security income ratio of the state, right? So it's a nice way if we don't have a lot of additional control variables or data to eliminate important omitted variable bias. Right? Just for the sake of time, we're kind of getting close to the end. I'll kind of also just show you a shorthand, and then we'll focus on some of these examples more next class. So this is the exact same one we did today, and we'll use some of the other ones next class. You don't always have to go through and do this stage by stage. I think it's good originally, and sometimes it can be helpful just to like think about what you're doing, especially in the context of like, if I was asked additional questions on that, not just getting the final result. But there's also a built-in instrumental variable regression. So IV regress and then 2SLS, that's all we'll be using for this class. There's some other options, but outside of the scope of what we're going to do. You're first going to tell it what you want your Y variable to be. And I kind of try to write this out up here. Then what is your X variable that you're going to use an instrument for? Ours was whether or not they had health insurance. What is the instrument that you're going to use? Equals that Social Security income ratio. And then what other additional controls do you want to throw in there? Okay. Now, if I run this regression, it should then just give me the results of my second stage. So if I go ahead and do this, sure enough, I get the exact same results here. Okay. I get the exact same coefficient estimate here as I did down here. Now, what you can do is if I throw in first on the end of this IV regress, just so you don't think like if I use this command, I can never look at the first stage results. This would show me the first stage results as well. All right, so it would show me both. Just the default is to just only show you the end result. But if you throw in that first command, it's also going to show you what that first stage is. And if we scroll back up, that should be the same as when we ran the first stage manually. Sure enough, that coefficient negative 0.19 is what we found from that first stage. So throwing in that first command allows you to look at both the first and second stage. We usually typically don't need to do that because we just care about what that unbiased coefficient is we get from the end result in that second stage. Okay. So next class, I've got another example we'll use from this data set. I've got some wage prediction examples, and then I've got some IQ examples. So I'll also bring, like I said, some papers if we have time, just to kind of give you an idea about some unique instruments that people have used in the past. This gets kind of fun. People use some weird ones. In fact, you're a captive audience. There's a great old book called Freakonomics. Let's see if it comes up pretty quickly. I'll have to look it up and bring it into next class, but they've got some real weird instrumental variable example, and now I can't remember what it is off the top of my head because I'm getting older and forget some of these. But I'll have a couple of these examples we'll kind of think through. We'll look through a little bit more how we do this in Stata and talk a little bit more about what we're doing with instrumental variables, kind of the math behind it, although I'm not going to expect you to like really push it too far in terms of giving me any mathematical support, right? So when we're thinking about the final exam, kind of like the quizzes, things we've looked at, you know, hopefully the first exam was a good indicator. A lot of it's going to be looking at output and how do we use that output, okay? All right. Any other questions for me before we get out of here? All right, so one more in-class quiz Thursday. Other than that, review next week, and I will see you guys on Thursday.